Okay, thanks for the invitation and organizing this series of seminars. So I'm gonna continue Guohang's talk, and but I will also talk about like how like the Hausdorff dimension and the geometric features that we see in these Nabonnand examples, how these things are related to the fundamental group of the manifold. So let's first have a quick recap of Guohang's talk in that talk, especially this example, right? So we take a Nabonnand-type example. This means we do this doubly wall product, and then we use warping function from Guohang's construction. And so here in particular, we're going to choose this FR grows like the square root of R, and then HR has a polynomial decay R to the negative alpha. And when this K, the severe part, K is sufficiently large, then this G has positive Ricci curvature. This is a example that has been known for decades. Then as Guohang said, so what we did is we look at the universal covering of this very old example, and we blowed it down to see what's the asymptotic cone of that. And we showed that it has rectifiable dimension 2, but the singular part has Hausdorff dimension 1 plus alpha, which could be exceeding 2. Now, to be honest, once you know this is the example to look to, then it's not too difficult to show that it satisfies these properties, to be honest. So I'm gonna say a few words on how did this example came to our attention. So this is one of the results during my thesis work is, let's say I have a complete Riemannian manifold of non-negative Ricci curvature. And I assume that the universal covering has a unique asymptotic cone as a metric cone. In particular, so if you have a manifold of, say, non-negative sectional curvature, this property is always satisfied. And under these conditions, so the result is the fundamental group is always finitely generated and virtually abelian. So I went to UC Santa Barbara for my postdoc study, and so I mentioned this result to Guohang, and then she told me that she had this example during her thesis work is you can construct a Nabonnand-type example, but to warp a new manifold. So it's really similar, kind of similar to the Nabonnand example, but instead of circle, or you say a manifold of non-negative Ricci curvature, here we do a new manifold with a family of Riemannian matrix, or with almost a flat matrix. And I'm gonna say a few more words on this construction later as well. And in particular, in this example, the fundamental group is a torsion-free nilpotent fundamental group, which does not have any abelian subgroup with finite index. So when you combine these two results, you list them side by side, and then you'll see that something peculiar is happening on the universal covering of M. For example, you can say that in this example, right, the universal covering, if you take its asymptotic cone, then either it's not unique, it must be not unique as a metric cone. While on the other hand, this is a pretty nicely constructed example. There's no like gluing happening there. So, I mean, the reasonable guess is that the asymptotic cone should be unique, but somehow it's not a metric cone than what it is, right? So that leads to us to take a look at the Nabonnand example first, because that's an easier form of this nilpotent one. Okay, so now let's take a closer look at the Nabonnand example. So we have this doubly wall product, and the important feature here is this HR is a decreasing function. So as reflected, why do I I don't have the pointer somehow, but anyway. So HR is it tells you how the circle shrinks as this R goes to infinity. And if you set a point, base point P at R equals 0, and you consider the fundamental group, which is just Z, and for each element, say gamma to the K, where this gamma is the generator of your fundamental group, we can draw these minimal representing loops. So in other words, at your base point P, you draw a loop that represents gamma to the K, but it has the minimal length. Now, because this H function H is decreasing, so when you draw this CK, it'll go into the end, loop some rounds there, and then comes back. So it more or less looks like this, right? And if you further assume that this warping function H has polynomial decay like R to the negative alpha, then you can do pretty simple estimates to show that all these representing loops, again, this is a P, and a CK may look like this. CK is the minimal representing loop for gamma to the K. And you can estimate that the length of this CK and the size of CK, they are all proportional to K to this power. So here size means we have this loop like this. So this is my P. Then let me use a different color. And then you draw a ball. You draw a metric ball at centered at P to include this loop. Then the smallest radius you can put there to include this loop is the size. So that's the size. Now, if you translate this to the universal covering, so maybe I continue to draw here. If you translate this property to the universal covering, it will be like you have these orbits here. So these are gamma dot p tilde, where p tilde is a lift of p, gamma is the fundamental group. Then you have a point, say gamma to the k p tilde, right? So then this tells you the length of this is proportional to k to this power. And moreover, this size is gonna tell you how much away is stray away from the orbit. So the picture more or less look like this. Now, with this picture in mind, when you blow it down, so then these orbit points, they get closer and closer, and the forms and limit our action. But the minimal geodesy is gonna keep staying away from your limit orbit. Yeah, so when you blow it down, you have this gy, so that's the limit of gamma p tilde. So this is gy, and it's an isometric R orbit, and the distance there. So this is y, this is ty. The distance still has this feature. It's like t to this power, and the minimal geodesic will go away from your limit orbit and comes back. Now, in particular, we say this is not convex, right? And we can show that this part has Hausdorff dimension 1 plus alpha. So let me pause here a moment. Any questions so far? Okay. So I want to say a few more words on this geometric feature that is what we see in here, the minimal representing loop. There are two features here. One is the minimal representing loop, that they go away from any bounded sets as you exhaust all elements in the fundamental group. The other feature is in the asymptotic cone, you have a non-convex orbit, and the Hausdorff dimension is strictly larger than 1, and could be very large if your alpha is large. And the other thing that we want to make a connection is, again, these two results that we listed side by side before is how does the fundamental group play a role here? because if we assume the universal covering is a unique asymptotic asymmetrical, it is virtually abelian. While in the Nabonnand-like, we have a nilpotent fundamental group. Does these geometric features plays a role in the distinction of, say, a fundamental group being abelian or torsion-free nilpotent? Okay, so let me say a few words on this so-called escape phenomenon. It means the minimal representative loop of your fundamental group can escape any bounded sets, as we see in Nabonnand's example. So for non-negative sectional curvature, it's a consequence of the source structure that this phenomenon will not happen. So all the minimal representative loop will stay in a bounded set, regardless what's your base point be. And the second thing is the fundamental group is always virtually abelian. Again, this follows from the source structure because your whole manifold is homotopic to a closed submanifold of non-negative sectional curvature. So the fundamental group didn't change. For closed manifold with non-negative sectional curvature, the fundamental group is always virtually abelian. So this will be the same as the fundamental group of the soul. Then it follows. And let me also mention that for non-negative Ricci curvature, we have this result developed over the years. Eventually, we can say that the fundamental group is CN nilpotent, which means that there is a subgroup of index at most CN. So this means index at most CN, and that is a nilpotent subgroup. Now, Mino first showed that the group, if it's finitely generated, then it has polynomial growth. Then Gromov showed that if you have a finite generated group with polynomial growth, then it must be virtually nilpotent. So in particular, one can say that any finitely generated subgroup of the fundamental group is virtually nilpotent. Then Couple-Wilkin finally showed that you have this index bound CN that it only depends on your dimension. And now, and we have seen in Guofang's example that in general, you do have torsion-free nilpotent fundamental group. So it cannot be further be improved to, say, virtually abelian. Now, if you add this condition, so you basically you take this property, right? All the minimal representative loops they are contained in a bounded set. You just artificially add this condition to non-negative Ricci, then it follows from Trigger-Gromov splitting theorem that the fundamental group is indeed virtually abelian. So from this result, you can see that your fundamental group whether being virtually abelian is related to where these minimal representing loops are positioned in your manifold. On the other hand, this artificial condition, I mean, you say that they're all inside a bounded set. This is a very strong condition, a very restrictive condition, I would say. Because if you have positive Ricci curvature and you assume the fundamental group is an infinite group, for example, Nabonnand's example, that's a positive Ricci curvature and the fundamental group is safe. Then it also follows from Trigger-Gromov splitting theorem that these loops, they must escape. They cannot be contained in any bounded subset. And let's also take a look at Guofang's example. So that's where you have positive Ricci and torsion-free nilpotent fundamental group. So in particular, let's recall that nilpotent is the next best thing you can have after being abelian, which means after doing finitely many commutators, eventually you get identity. A very simple example that we're gonna always use as our motivating example is this discrete Hessenberg 3 group. You take the upper triangular matrices, these ABCs as integers, then this is a torsion-free nilpotent group. It's not virtually abelian. The largest abelian subgroup you can have there is like Z square, which has infinite index in N. Now, so here is Guofang's construction back in the day. So you take this n tilde to be a simply connected nilpotency group. For example, you take the Hessenberg 3 group, but ABC in R. And then you take a lattice in that. So basically, now you take ABC as integer value. Now it is well known that the quotient, which we so called a new manifold, the quotient that does not admit a metric of non-negative Ricci curvature because the fundamental group is a torsion-free nilpotent group. But it's well known that these new manifold they admits a family of almost flat matrix. So that's being very close to flat. So here we will require that it has a parameter r, and as r goes to infinity, both the sectional curvature and the diameter of n goes to 0. And with this, then with a suitable FR and with this family of almost flat matrix on n and a sufficiently large k, then we can construct this warped product. So it's like a doubly warped, but this n is not like just differing by a scaling. It has this multi-step scaling that decays at different rate for different steps of your nilpotency. And then it has positive Ricci. The fundamental group is torsion-free nilpotent group. And you can also see the escape phenomena easily here because this diameter goes to 0. So you still have this Nabonnand-like feature that the minimal representing loops, you can go into the end to shrink its length so that it'll escape any bounded sets eventually. Now, motivated by these examples, so I introduced this notion called escape rate. Basically, we want to we want to quantify how fast this escape phenomena is happening there. So if we take a complete Riemannian manifold and we assume the fundamental group is an infinite group, then we define the escape rate by comparing the size over length. So this is a quotient, the size of C gamma. C gamma is a minimal representing loop for gamma element, and we compare it to the length. So such size again is your C gamma look like this. It's based at P. So the size is you draw a metric ball to include that. And as a convention, when a fundamental group is finite, we just set the escape rate as 0. And then we take the limit sup, right? So after taking this quotient, we take the limit sup as we exhaust all the elements in a fundamental group. So because size is at most 1/2 the length, because it's a loop, it goes forward, it needs to come back at a certain moment. So the escape rate is always less than or equal to 1/2. And by result of Sommerly, although she didn't use this terminology, is if your fundamental group is infinitely generated, then you can take these Gromov short generators, and then their minimal representing loops will be minimal up to halfway. Then minimal up to halfway just means size is exactly the length. So yeah, so basically, if infinitely generated, then you can take these minimal representing loops such that size of Ci over the length of Ci is exactly 1/2. So that in particular tells you the escape rate is 1/2, right? So that's like the extremal case you can happen for loops going very far away. Now you take the contrapositive of that. So if the escape rate is strictly less than 1/2, then the fundamental group is finally generated. And let me also mention that the recent example by Brie Neighbor Simola, where they give this counterexamples to the Miller conjecture, is you have an infinitely generated fundamental group. So in particular, their examples, the escape rate is going to be 1/2. Okay, so Yeah, so we introduced this notion because we want to capture how fast these loops escapes, right? So in particular, if they're already containing a bounded set, or they escape at a sublinear rate compared to their length, then the escape rate is zero. And also escape rate being zero does not depend on your base point. And in the Nabonnand-type examples, now, depending on how this HR decays, we can estimate the escape rate easily. So if your HR, so essentially is that the faster your HR decays, then when you draw the minimal representing loops, you're gonna take further advantage of that decaying length of the circles path. So your minimal representing loop should go further into the end. That will result in a shorter length and a larger side, the larger escape rate. So if the warping function here, HR, decays to a positive constant, then the escape rate is zero. If it decays like a logarithm function, then the escape rate is also zero. If HR is polynomial decay, now in particular, this is the one with positive, with big Hausdorff dimension, this will give you a positive escape rate. And then lastly, if you put HR decays like exponential. Now, however, if you require HR to decay like this, you're not gonna have non-negative Ricci curvature, all right? So in this case, the escape rate goes big, and it's actually the maximal one half. And for the polynomial ones, if your alpha is very, very large, as it goes to infinity, the escape rate also goes to one half. But alpha goes to infinity will also require your dimension m will also goes to infinity, by the way. So at least in these examples, that's the case. So if you fix your dimension, then this alpha cannot be too big. And the Guohang's construction, where you have this total-free nilpotent fundamental group, that the escape rate is away from zero, in the sense that you cannot tweak the parameters there so that it gets close, arbitrarily close to zero. And one of the open question that I have is, suppose I assume the fundamental group is finitely generated. For example, let's say it's just Z, for example. Does that imply the escape rate is strictly less than one half? So that would be like the converse of the previous property that I mentioned. If you have escape rate strictly less than one half, then it's finitely generated. So this asks whether the converse is true. You assume it's finitely generated. Does that imply escape rate cannot be one half? Any questions at this moment? Okay. So this is a result that I got during my postdoc time at Santa Barbara. So if you have complete manifold non-negative Ricci curvature, and if we assume the escape rate is very small, then the fundamental group is must be virtually abelian. So this somehow this generalized the previous result that I mentioned. So if all these minimal representing loops are staying a bounded set, then it's virtually abelian. Now we allow them to escape, but as long as they escapes at a slow rate, you're still gonna have this virtual abelian. Now the proof of this result goes to the so-called equivariant asymptotic cone is on the universal covering. You take a sequence I to infinity, and then you blow it down. So then you can have a convergent subsequence converges in the so-called equivariant Gromov-Hausdorff convergence goes to some limit. Now, one of the issue or the difficulty here is, in general, this limit is not unique. even the space, this Y is not unique, then the group action surely can be non-unique as well. So we're gonna take all these equivariant asymptotic together, and we call this omega m tilde gamma. Just take all the possible equivariant asymptoticals. If you have non-negative sectional curvature, then you do have uniqueness on these equivariant asymptotic cones. And in that case, this capital Y must be a metric cone with y, small y as the vertex. And moreover, the limit orbit gy, it must be a Euclidean subfactor in your space. If you have non-negative Ricci curvature, so then in general, this, as I mentioned, this capital Y, it may not be unique, and it may not be metric cones at all. Now, the sketch for the zero escape rate case is starting from zero escape rate. We show that the limit orbit is always convex. Now you should compare this in the Nabonnand example that the gy is not convex. If you take this h decays like r to the negative alpha, and once you get convex, then well, this is actually harder than the first step. So you need to show that it's not only convex, but it's actually a Euclidean factor inside Y for all. So these are the properties that holds in all the equivariant asymptotic cones. Then this property, being Euclidean factors, always being Euclidean, this actually implies virtual abelianness, and I'll talk about this part later. Why 2 implies virtual abelianness. But well, the takeaway is the proof. To prove this, you go to the equivariant asymptotic cones. You get a certain uniform properties there, and then you come back to say your property for the fundamental group. So. Okay, so now we take a revisit to Guofang's example and say what are the asymptotic cones of these examples look like, right? So we take a complete Riemannian manifold. So okay, so this is Guofang's example. Complete Riemannian manifold fundamental group is the Hessenberg 3 group. So maybe I should write this here. And then we take its universal covering, and we ask, okay, how's the asymptotic look like, right? So this again goes back to one of the first slides that we listed these two results side by side, because it shouldn't be a metric cone. So it turns out that this capital G is the three-dimensional simply connected Hessenberg group, and the orbit is always not convex. And also, if you take the center of G, so this H is like 11100 C inside R. Inside G. G is the Hessenberg 3 group. If you take the center and you consider its orbit, then this part, well, H is isomorphic to R, by the way, that's clear. Then its orbit will be homomorphic to R, but the Hausdorff dimension is at least 2. So this is kind of related to one thing is in the Nabonnand example, if that H decays like R to the alpha, then you know that in the limit, the Hausdorff dimension of the singular set is 1 plus alpha. So on one hand, we see that this alpha is related to how fast this H decays. On the other hand, we see here that it seems that this Hausdorff dimension is related to the nilpotency step here, because the Hessenberg 3 group has nilpotency step 2.
Can I ask a quick question? So in this, the H is the warping factor acting on the S1 in the Nabonnand example, right? But in the
So
way example, the scaling
H
of the
is a
difference.
H is R subgroup. This is in the limit. So H acts on the asymptotic cone.
I'm sorry, the little h,
The little
the
h.
warping, the
Oh yeah,
warping
yeah.
function.
The little h is the warping function. So that's the little
So
h is
it
the warping function.
right. So the warping function, little h, is the one that acts on the S1, right?
Yes.
In the Nabonnand example, and in the way example, how does it work? What are the two again?
So okay. So in Guofang's example, basically you have different h for different
Right,
generators of your fundamental group of say n.
right. So do
Then
you need all of them to be like negative r to the negative alpha?
yeah, it'll be like to some r to the negative power. But there's a relation between these powers for different steps.
Oh,
Okay. So the question from here is can so here I listed three properties. They're all about things happening at infinity, right? So can any of these asymptotic properties capture the structure of fundamental group, whether it being virtually abelian or being torsion, say, or the nilpotency step, things like that. Now, let's reformulate more precisely here. So, for example, let's assume that in all the asymptotic cones, this limit group G is always abelian. Does that imply, does this imply, say, pi 1 m is virtually abelian? So this corresponds to the first property here. So in Wei's example, you always have three-dimensional simply connected Hessenberg group if you start with a torsion-free nilpotent group. Now, if you assume they're abelian, does that tell you the fundamental group should be abelian as well? Now, the second thing is, if we assume all the orbits are convex, because in Guofang's example, if you blow it down, they're non-convex. If you assume they're all convex, does this imply the fundamental group is virtually abelian? And actually, the answer we already seen is yes, because escape rate being zero will be equivalent to say that all the limit orbits are convex, and that tells you it's virtually abelian eventually. Now, the third thing is the Hausdorff dimension of an isometric R orbits at Y somehow related to the nilpotency step. So let me first say that if you assume non-negative sectional curvature, then one is always true. The limit group is always virtually abelian, actually. And the orbit is always convex. It's actually Euclidean factor. So one and two, they're all true. And moreover, the Hausdorff dimension of any isometric R orbits in the limit, they must have Hausdorff dimension one, because that's happening inside a metric cone. Because if you have non-negative sectional curvature, you blow it down, it's a metric cone. On a metric cone, you're not going to have crazy things happening over there for R actions. And let me also point out that the first condition actually does not imply virtual abelianness, because it turns out that we can modify Wolfram's construction so that even you start with your group as a Hessenberg 3 group, but the limit group is always isomorphic to the abelian R3 in all asymptotic limits, right? So somehow the group structure, this nilpotency, is may not be reflected in these algebraic limits. So like this G, it becomes abelian now. So you lost the information there. So in the paper, in the joint work with Guofang, where we constructed this examples, large Hausdorff dimension, we raised this question: is the nilpotency step of the fundamental group somehow related to the Hausdorff dimension of some isometric R orbits in the asymptotic form of the universal covering? Now, let me give more context here, and this is also actually related to the so-called chiral group. So let me first give some definitions for context. So let's take a finitely generated torsion-free nilpotent group. And then it has this lower central series. So basically, Ni plus is you take the commutator between N and I. Then we say the step of N is the smallest integer such that you end in identity after error many times commutation, a commutator. For example, the Hessenberg-3 group nilpotency is step 2. Well, abelian group has step 1. So if our fundamental group is a finitely generated and virtually nilpotent group, then you can always find a torsion-free one inside it with finite index. And then you can use that torsion-free one to define the step of your larger group, and it is well defined. So this is partially why we require it to be torsion-free, all right? If you don't take a torsion-free one, then you're not gonna well define the step for a virtually nilpotent group, right? And in particular, this definition applies to a finitely generated fundamental group with non-negative Ricci curvature, because we know it must be not only virtually nilpotent but C nilpotent. So we can talk about the step of pi1m. So that's essentially you take a torsion-free nilpotent subgroup of finite index, and you say, well, what's the step of that torsion-free nilpotent part? So yeah, this is also related to the chiral group. So this one does not have non-negative Ricci curvature. So you start with any closed manifold with an infinite fundamental group, and you also assume that the fundamental group is virtually nilpotent. For example, you can take I mean, there are a lot of examples. So in Gromov's work, so he showed that if you have a finitely generated group of polynomial growths, then it must be virtually nilpotent. So in that work, so that's where this Gromov-Hausdorff convergence, this idea first formalized. We applied it to blow down the group, and it will be equivalent to here to say to blow down the universal covering. And then later on, this is also studied by Pan-Su. So he described what are actually these limits. So here you have this m tilde p, you blow it down. So maybe I also draw the base manifold, but that didn't matter because this is a closed manifold. So here on the base, it always converges to a point. Then on here, it goes to some g e with some distance d. And there are very nice structure about this G, and it turns out this is also unique. This is unique actually. So it does not depend on your scaling sequence I. So the limit is a simply connected stratified nilpotent Lie group, capital G, with a left invariant subfinsler metric. This is so-called a chiral group. And the group structure of gamma, so that's your fundamental group. It's reflected in the limit, this capital G. So there are two ways to see the step of gamma here. So one is you can look at the step of G. Simply connected. Yeah, I said that. One is you can look at the step of G. So they must be the same. The second thing is you can look at the Hausdorff dimension of a R subgroup there. So if you take the air inside G, that is in the last non-trivial subgroup of your lower central series. So here you have G, then G0, right? G1, then G air minus 1, then G air is identity, right? So this air is the step of your G. If you take a non-trivial, if you take an R subgroup inside G air minus 1, then because your G has a distance function, right? So you can consider this air with this distance function. Then it turns out that so that this air is really an R subgroup, by the way. I'm taking an R subgroup. Then the distance function on there will be like p to the 1 over air, all right? So it'll have Hausdorff dimension exactly air as the step of your gamma. So there are two ways to see the step of gamma from infinity. You can either look at the step of your limit group, or you can look at the Hausdorff dimension of some R subgroup. Yeah, so combining this with the previous thing that I asked, like can you see the step of your fundamental group at infinity? So you can ask, what if you start with now not a closed manifold, but a non-compact one, right? A complete manifold with non-negative Ricci curvature. In what sense you can generalize these things? And in particular, we have already seen that the first one may not have a good generalization because you can have gamma is a torsion-free nilpotent group, but G becomes abelian if you start with a complete Riemannian manifold now. So this is the result. So that I got this year. So we start with a complete Riemannian manifold with non-negative Ricci curvature and an infinite fundamental group. And I need an additional assumption that the escape rate is not 1/2. So that recall that 1/2 is the maximal value you can go. So we assume the escape rate is not maximal. And in particular, this will imply that the pi1 is finitely generated, right? It's finitely generated, so the step of this makes sense now. Also makes sense. But it's virtually abelian. The result is you can always find there exists some asymptotic cone of the universal covering and a closed R subgroup of that G, so that the Hausdorff dimension of your orbit is at least the step of gamma. So in some sense, so the phenomenon that we have seen in the Nabonnand example, right? So that's where we said, okay, you blow it down, you have R orbits of large Hausdorff dimension, or say big Hausdorff dimension. In some sense, that phenomena is prevalent. So as long as you start with a torsion-free nilpotent fundamental group, you blow it down, then you can always see this feature in some of the asymptotic. And in terms of the whole group, so here is you take this this air as a subgroup of G air subgroup, R subgroup, but you can also talk about what is GY, right? The whole orbit. So if you take so again, the same assumptions, non-negative Ricci curvature, infinite fundamental group, and the escape rate is not 1/2. Then for any, so this holds for all, right? So here it is, there exists one. So for all equivariant asymptotic cone, the orbit has a natural structure as a connected and simply connected nilpotent group, and its step cannot exceed the step of your fundamental group to start with. So these two results combined together, you can see these two as a generalization of the closed case here, where you have closed manifold with a virtually nilpotent fundamental group. Then there's this relation. Here is really equalities between step of G, step of gamma, and the Hausdorff dimension of some R orbit. While here it becomes inequalities. So you have this, and these inequalities are sharp. So you can have examples that they are the same, and you can have examples they become the strict inequality. And So again, so another thing is here. So in a closed case, you get the limit is a group that is a simply connected stratified nilpotent group. So here we get it's a connected and simply connected nilpotent group, but it may not be stratified. A remark here is if you take the example by Brin-Neighbor-Simola, where you have this infinite generated fundamental group, you can have Q or Q mosaic. In their example, the escape rate is 1/2, and the limit of it can be connected. It can be disconnected or can be a compact one. For example, a circle. A circle as your orbit. So here, this is comparing to this result that if the escape rate is not 1/2, then the limit of it is actually it's always non-compact, and it's a simply connected nilpotent group, a connected one. All right. Any question at this moment? Okay. So now I'll say a few more words on how the nilpotency step is indeed related to the Hausdorff dimension and other distance estimates. So let's again take the discrete Hessenberg 3 group as an example. If you take an element gamma in the center, so again, you can take this gamma as say 0. Sorry, it's definitely not 0. 1, 1, 1, 0, 0, 1. You take this element, it's in the center of gamma. Then gamma to the m has word length that is comparable to the square root of m. So what word length is, you can take a generator. So generator is 1, 1, 0, 0. Basically this one. Beta is, sorry, that's a 0. Oops. And if you do commutator alpha beta, it will generate gamma. So, but if you want to say what is gamma m squared, then it turns out that you can use the commutator to write this m squared word by just using for m many words. Because that's a commutator, so that's why you get a 4 there. So in particular, if you have this gamma to the m, its word length will be comparable to the square root of m. So, but if you do this, so that, yeah. So, but on the manifold, you only have one-sided inequality, right? So this gamma to the m means, so here m is complete, is open. So let me say non-compact. If you have a closed manifold, then you have two-side inequality on the orbit. If you have an open manifold, non-compact one, then you just have one side. So that actually becomes a huge issue. Now, if you want to say a fundamental group is virtually abelian, one way to say it is virtually abelian is you find a lower bound for this length that contradicts this upper bound, right? Because yeah, so let's say you want to rule out that a Hessenberg 3 group can happen for a fundamental group. So if you can prove a lower bound for gamma to the m that violates this, then you get a contradiction. So you cannot be the Hessenberg 3 group. Now, in general, if you take a finitely generated torsion-free nilpotent group with nilpotency step air, then you have this word length is comparable to m to the 1 over air. And then in terms of the orbit on your universal covering, you only have one side bound. So there's c to the c times m to the 1 over air. Now go back to the previous result that we said if you have small escape rate, then it is virtually abelian. So before we mentioned that zero escape rate gives you limit orbits are convex, then it gives you limit orbits are standard Euclidean subspace. If you start with very small escape rate, then it turns out that these limit orbits is always very close to a standard Euclidean space in the Gromov-Hausdorff sense. Then, well, let's say to just say Euclidean subspace, then we can further show that there's so it acts on a Euclidean space, so it'll be like translation, it turns out. It'll be just be pure translation. Translation is like dh squared y is twice dh y, right? If your h acts as a translation at y. So then you can get almost to translation on your manifold at a large scale. So if you fix a very small epsilon, then this gamma square, so the gamma square is basically how your gamma moves. So this will be very close to twice of gamma with sufficiently large gamma. Sufficient large gamma because you are saying the asymptotic cone has this property, and then you're going back, so you need a large gamma. Now, but the takeaway here is okay. You take a gamma, so it'll grow almost like twice. Every time you take square, it's almost twice the distance. Now, on the other hand, if you have a say Hatchenberg 3 group, you have this gamma to the m should be less than or equal to c times square root of m. You always have this estimate if your gamma is the Hatchenberg 3 group, right? On the other hand, by this almost translation, you know that it should grow almost every time you double you twice. So that's a contradiction here. You cannot have, say, you double it, you get twice of that. On the other hand, you have this square root upper bound. Now, let me also say a few words on the Hausdorff dimension one. So you take an element in the last non-trivial central series, and we consider all the limits. So this gamma is in there, and you consider all the equivariant asymptotic limits. And so it turns out that this air y is always homomorphic to R, but this is actually highly non-trivial. So you need an escape rate is not 1/2 to prove that. And then you say, okay, I take all these Hausdorff dimensions and take the supremo of them. And this is indeed a max, by the way. This is indeed a max. So escape rate is not 1/2, and then with this notation, we can show that there is a lower bound on gamma to the m by using this d gamma, but by this Hausdorff dimension, that gives you a lower bound. And comparing to an upper bound that we could get from the group structure, 1 over air, and then we can get an inequality. So that tells you, that relates the Hausdorff dimension to the nilpotency step, basically. Now, one of the difficulty is we need to show that this air y, this limit orbit is indeed homomorphic to R in any asymptotic limits. And this limit orbit gy is essentially a singular set with very large Hausdorff dimension. And there's no such structural results unknown for these singular sets in rich limit space. And that's the difficulty there. Now, as a consequence, we can apply this to manifolds whose universal coverings are conic at infinity. So we say a manifold is conic at infinity if any asymptotic cone is a metric cone with vertex as your base point. And here we do not require the asymptotic cone to be unique. It can be non-unique. It can have different dimensions as well. And if you have a metric cone as a rich limit space, then you have trigger-coding splitting theorem. Then you have good description on how these R subgroup look like, because it will be actually in the Euclidean part. Then it turns out that the Hausdorff dimension of any R closed subgroup is always Hausdorff dimension 1. And now combining with go to previous slide, this one, right? So this would be like saying this is always one. If you have metric cones, then the step has to be one. So your group has to be virtually abelian, right? So that's a corollary. So if you have a complete Riemannian manifold, non-negative Ricci curvature, and the escape rate is not 1/2, if the universal covering is conic at infinity, then the fundamental group is always virtually abelian. And if the universal covering has Euclidean volume growth of constant air, positive, well, Euclidean volume growth is always positive, then it follows from the work by Trigger and Coding that all these asymptotic cones must be metric cones. And in this case, we can say a few more than virtually abelian, that we can bound the index of this abelian subgroup by some universal constant C in the air. N is the dimension and the air is the growth rate here. There's also this relation to small escape rate, right? So if you take a torsion-free nilpotent subgroup N, and inside the fundamental group, we find an index. And again, we take this gamma as the non-trivial element in the last non-trivial lower central series. So recall that we have said its limit orbit is always homomorphic to R, and this d gamma, which is the supremo of all these Hausdorff dimension of these orbits y, there it's at least the step here. And if the escape rate is small, then it turns out this d gamma must be very close to 1, as this escape rate going smaller and smaller, all right? And in particular, you can take a small epsilon so that this term is less than 2. Then it'll be virtually abelian. So that's the relation to the small escape rate is, if you have small escape rate to start with, then these are orbits has Hausdorff dimension very close to 1. While being torsion-free nilpotent, you have Hausdorff dimension at least 2 for some limit orbit. Okay, now I'll end my talk with some open questions. The first one I already mentioned is, if you assume the fundamental group is finitely generated, does that imply the escape rate is strictly less than 1/2? Because we already know the other direction is true. So this is like the converse. It's like the converse of that. Now, in other words, can we replace, say, escape rate not 1/2 this condition by just saying that the fundamental group is finitely generated? But that's another way to say it. Now, the next question is, what is the minimal dimension N so that a complete manifold, N manifold of non-negative Ricci curvature has a non-abelian torsion-free nilpotent fundamental group? And you can also ask what's the minimal dimension N K for step at least K. And from that relation to Hausdorff dimension, I mean the relation between Hausdorff dimension and the nilpotency step, a way to approach this is we ask this question: what is the minimal dimension N so that an RCD space, 0N space, admits an isometric R action of Hausdorff dimension at least 2 or at least K? So the best example we know so far is actually N equals to 10, but we don't know whether there's a reason behind it or whether you can find smaller dimension. All right, so for Hausdorff dimension 2, we have N equals 10 as our example. It seems optimal, but we don't know why. Now, the last question is about this escape rate hierarchy. Is instead of saying very small escape rate, you have virtual abelian, can we have a series of constant that can characterize the nilpotency step of your fundamental group. So how fast your escape rate is, then can control how many steps you have in your nilpotency. So yeah, so that's all of my talk, and thanks for your attention.